Okay, let's unpack this. Think about those mind-blowing things these large language models can do now. Amazing, right?
Absolute amazing.
But have you ever considered the sheer computing power
Yeah.
needed to make it all happen?
Oh, yeah, it's immense.
We're talking about massive data centers, huge energy bills, and top-tier hardware that puts this technology out of reach for many individuals and everyday devices. It's almost like needing a Formula One pit crew just to change a tire.
That's a really insightful analogy.
Yeah.
The resources required are a significant bottleneck, definitely.
Right.
It impacts not just who can use these models, but also where they can be deployed.
Exactly.
And this trend towards bigger and bigger models just makes it worse, right? Limits accessibility, raises environmental concerns.
Sure.
Imagine the possibilities if you could have, near state-of-the-art AI running efficiently on a smartphone, for example. That's the kind of barrier we need to break down.
Exactly. So what if we could get similar high-level performance without all that computational muscle?
Yeah, what if?
That's the fascinating question at the heart of our deep dive today. BitNet B1.58 2B4T. It's a new open-source large language model making some serious noise because it claims to perform on par with much larger models while being significantly more efficient.
And what's particularly compelling, I think, is that BitNet B1.58 2B4T is architected for efficiency right from the ground up.
Right, it wasn't an afterthought.
No, exactly. So our discussion today will delve into exactly how it achieves this impressive balance.
Okay.
We'll be drawing on the BitNet B1.58 2B4T technical report, which is available on our fourth. It gives a really detailed look at its architecture, the training process, and importantly, the rigorous evaluations.
So our goal for this deep dive, for you listening in, is to sort of demystify the technical details and really grasp what makes BitNet B1.58 2B4T so groundbreaking.
Yeah, cut through the jargon.
Exactly. We want to highlight those aha moments, How a model with 2B4T in its name, 2 billion parameters trained on 4 trillion tokens, can genuinely compete with the big players without those massive resource demands.
Okay, so let's start by really focusing on the core challenge that BitNet addresses, the substantial resource consumption of large language models.
Right, the problem is trying to solve.
As we touched on, deploying and operating these large, full-precision models, it carries a considerable cost. They need significant memory just to store the model's parameters. We're often talking many, many gigabytes.
And this large memory footprint, it has a cascade of consequences, doesn't it?
Yeah, it really does.
It means you need specialized, often expensive hardware like powerful GPUs, loads of RAM, plus all that processing, it just guzzles energy. This isn't just about your home electricity bill. For large-scale AI deployments, the environmental impact is, well, substantial.
Precisely. And then there's the speed factor.
Inference speed, right? Or latency.
Yeah, how fast these models generate text, the decoding latency. Larger, more complex models often take longer to process input and produce output.
And that delay can be a major drawback for applications that need quick, real-time interactions, like chatbots or virtual assistants.
Definitely. So these limitations ultimately restrict the use of powerful LLMs on, say, resource-constrained devices like smartphones or in areas with limited infrastructure.
Okay, so the issue's clear. Big models, they offer power, but demand significant resources. Now, the technical report introduces this concept of one-bit LLMs as a potential way forward. What exactly does that mean? Is it like a fundamental shift in how the model represents information?
In essence, yes. It's a pretty radical simplification of how the model stores its knowledge.
Okay.
Traditional neural networks use high-precision numbers, think decimals with lots of places, like floating point numbers to represent their weights. Those are the core parameters learned during training.
Right.
One-bit language models dramatically reduce the number of possible values these weights can take. In the most extreme version, they're limited to just 2 states, often represented as -1 and +1, so binary.
Binary.
Or sometimes 3 states, like -1, 0, and +1. That's ternary.
Okay.
This extreme compression significantly reduces the memory needed to store the model.
That makes intuitive sense. Fewer possible values means less data to store.
But, it sounds like a severe compromise. Wouldn't that fundamentally limit the model's ability to learn and capture the intricate nuances of language?
That has indeed been the primary challenge with one-bit models historically, yeah.
Yeah, okay.
Earlier attempts particularly those that involve taking a pre-trained full-precision model and then compressing its weights down to 1 bit after training. It's called post-training quantization.
Right, PTQ.
Exactly. Those often resulted in a noticeable drop in performance. The models got smaller and faster, sure, but their accuracy and ability to understand and generate complex language suffered.
So big trade-off.
A big trade-off. And there have also been native 1-bit models, meaning they were trained from scratch with these highly restricted weights. But these tended to be smaller in scale and haven't historically matched the capabilities of the larger, full-precision models. So while the efficiency benefits were appealing, that performance gap was a major obstacle. Okay, so that provides crucial context. We have these highly efficient, but historically, let's say, less capable 1-bit models. And now, bitnet B1.58 2B4T enters the picture. The report calls it a breakthrough. The first open-source native 1-bit LLM at the 2 billion parameter scale, trained on a massive 4 trillion tokens. That word native seems really significant here.
It is absolutely key. The fact that bitnet B1.582B4T was trained from its inception with a focus on these low-bit representations is what sets it apart.
Right.
It wasn't a full precision model squeezed down later.
Sure.
This allowed the researchers to tailor the architecture and the training process specifically to function effectively within these constraints. The explicit goal was bridging that efficiency-performance gap we just talked about.
So how do they actually pull this off? What are the core architectural innovations that let this 1-bit model perform so well relative to its size?
Well, the foundation of bitnet's efficiency lies in its custom bit linear layers.
Okay.
These replace the standard linear layers you find in a typical transformer architecture. And within these bit linear layers, there are several noteworthy innovations.
Like what?
First is the weight quantization. Instead of going all the way to pure binary, manacle 1 and +1,
Yeah.
bitnet uses what they call 1.58-bit weights during the forward pass.
1.58-bit. How does that work?
It means the weights are quantized to 3 possible values, manacle 1, 0, and +1, so ternary.
Ah, ternary. Okay, so the 0 is the key difference there.
Exactly. And they use an absolute mean or abs mean scheme to figure out these ternary values.
Abs mean.
Yeah. This seemingly small deviation from pure 1-bit can actually have a surprisingly large impact on the model's ability to represent information effectively.
Interesting. So ternary, not strictly binary, that inclusion of 0 must offer some added flexibility, right, in representing the learned relationship.
That's the idea.
And they mentioned abs mean, if I understand correctly. That's basically looking at the average magnitude of the weights in a layer to decide the thresholds for quantizing them to -1, 0, 0, +1. Is that roughly it?
You've got the right idea. Essentially, for each weight tensor in a layer, they calculate the average of the absolute values of all the weights in that tensor.
Okay.
This average then serves as a kind of dynamic threshold. It helps determine whether a particular weight should be mapped to -1, 0, or +1.
Right.
This adaptive quantization strategy helps the model retain crucial information while still getting that significant precision reduction.
Okay, so that covers the weights. What about the activations, the signals flowing through the network during computation? The report mentions they use 8-bit integers for those. That's higher precision than the weights. Why the difference?
That's correct. While the weights get this aggressive quantization, the activations are represented using 8-bit integers. This decision likely reflects a careful balancing act. You want to maximize memory savings through weight quantization, but you also need to ensure sufficient signal fidelity as information propagates through the network.
Makes sense.
If you quantize the activations too much, that can also lead to a substantial drop in overall performance.
Right.
The ABSMAX strategy they use for activations means that for each individual token being processed, they find the absolute maximum value within its activation tensor and use that maximum value to scale all the activation values for that specific token down into the 8-bit integer range. This per-token scaling helps handle the potentially wide dynamic range of activations.
That makes sense. And you need enough precision in those signals to effectively use the information encoded in those highly quantized weights.
Precisely.
The report also mentions sublin normalization. That sounds like a specialized technique. What's the benefit there?
Sublin normalization, it's short for sublayer norm. It's a specific variation of the common layer normalization technique. In the context of bitnet, its main role is to enhance training stability. Training with highly quantized weights can sometimes be, well, more prone to instability compared to full precision training.
Right, I can imagine.
So normalization techniques like sublin help smooth out the learning curve and prevent the model from becoming unstable during training.
Yeah, and they also made an interesting switch in the activation function inside the feed-forward network. They moved from the more common 3LU to squared ReLU, or ReLU squared.
Yeah, ReLU.
They suggest this might encourage sparsity and offer computational advantages in a one-bit context. How does that work?
So squared ReLU, which is just the ReLU function applied, and then squared max 0x squared, it has this property of pushing more activation values towards exactly 0.
Ah, okay.
In a one-bit model where computations involving 0 can potentially be done very efficiently, this induced sparsity can lead to further speed improvements during inference.
I see.
It also potentially aligns better with the characteristics of the ternary weights, creating maybe a more harmonious interaction between weights and activations.
The report also touches on some more standard components, like rotary position embeddings, rope E for handling word order,
Standard stuff there.
and the notable decision to remove bias terms from both the linear and normalization layers. Why get rid of biases?
Removing bias terms is a design choice seen in other efficient architectures too, like LLM.
Nope.
It basically serves to reduce the total number of trainable parameters in the model, which directly helps with its smaller memory footprint.
Makes sense.
It can also simplify the quantization process a bit. While bias terms can be helpful sometimes, the researchers likely found they could achieve comparable performance in this specific one-bit architecture without them.
And lastly, regarding the sort of fundamental building blocks, they're using the LLM-A3 tokenizer. That seems like a smart move for compatibility and handling diverse text and code.
Oh, absolutely.
That vocabulary size, over 128,000 tokens, is pretty standard for modern LLMs.
Exactly. Using a well-established and widely adopted tokenizer like LLM-A3's ensures bitnet B1.582B4T can effectively process a broad range of text and code data.
Right.
And it means it can seamlessly integrate with existing tools and workflows in the open source AI community, which is a big plus.
Okay, so we have a good handle on the architecture now. Let's delve into how they actually trained this model. Training a one-bit model from scratch on, 4 trillion tokens. That sounds like an incredibly complex undertaking.
It certainly is a significant endeavor. The training process was structured into 3 distinct phases: pre-training, supervised fine-tuning, SFT, and then direct preference optimization, DPO.
Okay, 3 phases.
Interestingly, the researchers mentioned they didn't use reinforcement learning techniques like PPO, which is often used to fine-tune LLMs for specific behavior.
Right, RLHF.
Yeah. But they do identify this as a potential area for future work.
Gotcha. Let's start with that initial pre-training phase. They used a 2-stage learning rate schedule. What's the thinking behind that approach?
The 2-stage learning rate schedule is a pretty common and effective strategy when training these really large neural networks. The first stage typically uses a relatively high initial learning rate, coupled with a standard cosine decay schedule. The researchers noted that one-bit models seem to have more stable training dynamics, which let them use a somewhat more aggressive initial learning rate.
Ah, interesting.
Then the second stage, often called a cool-down phase, starts around the midpoint of training. At this point, the learning rate is abruptly dropped to a much lower peak value, and then it also follows a cosine decay.
Okay, so a sharp drop, then decay again.
Right. This cooldown period lets the model further refine its learned representations, potentially focusing on higher quality data during that phase.
And they also implemented a matching 2-stage weight decay strategy during pre-training.
Yes, in that initial phase, they used cosine-based weight decay. That's a form of regularization to help prevent overfitting, especially during that initial period with the higher learning rates.
Makes sense.
But then, during the subsequent cooldown phase, they actually disabled weight decay completely, set it to 0.
Really?
The idea there is that with the combination of the lower learning rate and the focus on curated data, the model's parameters can settle into more precise optima without needing that extra regularization push.
Okay, interesting trade-off. And what kind of data were they feeding this beast during that pre-training stage? 4 trillion tokens is a lot.
It is. The pre-training data was a diverse mix of publicly accessible text and code. It included large-scale web crawls like DCLM, that's a massive dataset of web documents and educational content from the FineWeb EDU dataset.
Okay.
To specifically boost its math reasoning, they also mixed in synthetically generated math data.
Ah, synthetic data too.
Yeah. And as we mentioned with the learning rate strategy, the data presentation was also staged. Most of the general web data was used in the first phase, while those higher quality, curated data sets were emphasized during the second cooldown phase.
We got it. So after pre-training, they moved on to supervised fine-tuning, SFT. This is where they teach the model to follow instructions better and have more coherent conversations, right?
Exactly. For the SFT phase, they used a collection of publicly available instruction following and conversational datasets. Things like WildChat, LMSYS Chat1M, WizardLM, Evil Instruct, Slamorca,
Familiar names.
yeah, standard benchmarks. And they also included synthetic datasets generated using methods like GLAN, likely some kind of adversarial generation and math scale, to further improve reasoning and handling complex instructions.
And they even detailed the specific chat template they used, with special tags like Bajinov text and eORDED to mark turns between the system, user, and assistant. It's impressive how much detail is in the report.
It's very thorough.
What were some of the key optimization decisions during this SFT phase? Anything different because it's a one-bit model?
Yeah, one noteworthy thing was how they calculated the loss during training, instead of the more typical approach of averaging the cross-entropy loss across all the tokens in a batch.
Okay.
They found that summing the losses actually led to better convergence and ultimately better performance for this particular model. Empirically worked better. They also observed they needed to use a relatively larger learning rate and train for more epochs during SFT compared to what you might normally see when fine-tuning full precision models of a similar size.
Ah,
So we suggest the optimal training dynamics for a one-bit model might have some, distinct characteristics.
right. You can't just use the same recipe. Finally, after SFT, they use direct preference optimization, or DPO. This is another technique to align the model's behavior with human preferences, helpfulness, safety, and it's often seen as more efficient than traditional reinforcement learning from human feedback, RLHF.
That's correct. DPO lets them directly optimize the language model using preference data, where humans have basically said, this response is better than that one.
Okay.
They use the ultra feedback and magpie datasets for this preference training, providing a diverse range of human judgments.
Right.
They trained for a relatively short time, just 2 epochs, with a specific learning rate and a beta parameter that controls how much the model deviates from its SFT trained state.
Yeah.
They even used optimized kernels from the Liger kernel library to speed up this DPO phase.
Nice.
And their qualitative observations suggest that DPO did a good job refining the model's conversational abilities and alignment without messing up its core knowledge and skills too much.
Okay, so we've covered the architecture, the training. Now for the really critical part, how well does it actually perform? The report has a ton of evaluation results across different benchmarks.
Indeed. They really put bitnet B1.58 2B4T through its paces, a comprehensive suite of evaluations covering everything from basic language understanding and reasoning to world knowledge, reading comprehension, math, code generation, and even instruction following and conversation quality.
Wow, broad coverage.
Yeah, they used well-established benchmarks like ARC Easy and ARC Challenge for reasoning, MMLU and Truthful QA for knowledge, GSM-8K for math problems, Human Evil Plus for coding, and MT Bench for conversation quality.
And they compared it against other open-weight, full-precision LLMs of about the same size, right? Like Llama 3.2 1B, Gemma 3 1B, Cran 2.5 1.5B.
That's right.
So what were the big takeaways from that comparison?
Well, the most striking finding is bitnet B1.58 2B4T's incredible resource efficiency.
Yeah.
Its non-embedding memory footprint is just zero.4 gigabytes. It's tiny, substantially lower than all the full precision models they compared it to.
Wow, 0.4 gigs.
They also estimated its energy consumption during decoding to be significantly lower, and it showed faster CPU latency.
Okay.
This really highlights the potential for major cost savings and, crucially, the ability to deploy this level of AI on less powerful hardware.
Right, that small memory footprint is key for devices with limited RAM. It could really democratize access.
Exactly.
But obviously, efficiency is only great if the performance holds up. How did it actually do on those benchmarks in terms of accuracy and capabilities?
Impressively well, actually. The report shows that bitnet B1.58 2B4T achieves performance that is on par with or even better than these full precision models on a significant number of the benchmarks.
Oh, better.
Yeah, for instance, it got top scores on several reasoning, knowledge-based, and math problem-solving tasks.
Huh.
Now, some of the full precision models might have a slight edge on very specific tasks, or maybe in the overall average across all benchmarks.
Sure.
But BitNet B1.58 2B4T delivers really strong and competitive performance across the board. It genuinely seems to achieve nearly the same level of capability with just a fraction of the computational overhead.
That's a real aha moment, isn't it?
Yeah,
Comparable power, way less resource demand.
it really is.
That's a huge achievement. What about when they compared it to other models that were quantized after training down to INT4 precision, like that Quinn 2.5 1.5B model?
Yeah, that comparison further strengthens the case for BitNet's native low-bit approach.
How so?
While post-training quantization does reduce the memory footprint of full precision models effectively,
Right.
BitNet B1.58 2B4T still has an even lower memory requirement because of its inherent one-bit design, but more importantly, it maintains stronger overall performance compared to those INT4 quantized models.
Wow.
This suggests that training a model from the get-go with low bit weights might be a more effective strategy for hitting that sweet spot of efficiency and performance, rather than just trying to compress a fully trained, high-precision model afterwards.
Okay, native training seems to have an edge over post-training quantization, at least here. And finally, how does BitNet B1.582B4T compare against other open-weight models that are also low-bit, either natively trained or quantized down?
This is where BitNet B1.58 2B4T really stands out as a leader in the open-weight one-bit space.
Okay.
The evaluation results clearly show it outperforming other natively trained one-bit models, even smaller ones. But perhaps even more impressively, it also outperforms much larger models that have been post-training quantized down to a similar 1.58-bit precision.
Wow, even larger models quantized down.
Yeah. This really underscores how effective their native training methodology is. It seems to have unlocked a new state-of-the-art for models running at this extreme level of quantization.
It suggests the way they trained it is key to getting this performance at such low precision. So it's not just about saving space. It feels like this native one-bit training approach actually unlocks something special in balancing performance and efficiency at that precision level. Now, achieving this efficiency in theory is one thing, but how do you actually run it efficiently on real hardware? The report talks about inference implementation.
That's a crucial practical point, yeah. The W1.58A8 scheme, 1.58-bit weights, 8-bit activations, it isn't something standard deep learning libraries are automatically optimized for.
Right, custom.
So the researchers developed custom inference solutions tailored for both GPUs and CPUs. And really great for the community, they've open sourced this code.
That's fantastic. For GPUs, they made a custom CUDA kernel. That sounds pretty technical. What's the basic idea behind optimizing it?
Well, since you can't directly store and process these ternary weights efficiently using standard data types on current GPUs,
Right.
they use this clever pack, store, load, unpack, compute strategy.
Pack, store, load, unpack, compute.
They essentially pack multiple weight values, Magoiro plus 1, into a single 8-bit integer just for storage in the GPU's main high-bandwidth memory.
Ah, to save bandwidth.
Exactly. Then, when those weights are needed for computation, the custom CUDA kernel loads these packed values into the GPU's faster on-chip memory, unpacks them back into their usable ternary form, and then does the matrix multiplications with the 8-bit activations.
I see.
This approach minimizes the data transfer between the slower main memory and the faster on-chip memory, which is often a major bottleneck in GPU work.
Smart.
They also point out, though, that current GPUs aren't ideally designed for one-bit models, hinting that we could see even bigger efficiency gains with future hardware specifically built for low-bit computing.
Future hardware potential. Okay. And for people who might not have high-end GPUs, they also developed a C++ library called bitnet.cpp for CPU inference. That's a big step for accessibility.
Absolutely. Bitnet.cpp provides highly optimized kernels specifically designed for standard CPU architectures. It's engineered to work efficiently with BitNet's unique quantization scheme and aims to give fast, accurate inference for these 1.58-bit models directly on CPUs, no special hardware needed.
That's great.
And the fact that they open source this library as a reference implementation is a really valuable contribution, making this tech much more available for people to experiment with and build on.
Okay, so to bring it all together then, what are the absolute key takeaways from this deep dive into BitNet B1.58 2B4T?
Well, the central takeaway is that BitNet B1.58 2B4T represents a genuinely exciting advance in large language models.
Hmm.
It's the first open source, natively trained 1-bit LLM at this 2 billion parameter scale, and it has convincingly shown it's possible to get performance comparable to leading full precision models of similar size while needing dramatically fewer computational resources.
Lower memory, less energy, faster speeds.
Yeah, exactly. Lower memory footprint, less energy consumption, faster inference speeds. And furthermore, the open release of the model weights and the optimized inference code for both GPU and CPU is a huge step towards democratizing access to this kind of cutting-edge technology.
It really challenges that prevailing idea that high performance in LLMs requires these massive full precision architectures.
It absolutely does.
And the report also hints at some intriguing future research directions. What are they looking at next?
Yeah, they're currently exploring several promising paths. One key area is just scaling up, trying even larger 1-bit architectures and training on even bigger data sets to see if this performance parity holds or even improves at larger scales.
Right, does it scale?
They're also really interested in hardware co-design and optimization specifically tailored for low-bit computing. That could unlock even greater efficiency gains beyond what's possible today.
Makes sense.
Other areas include extending the model's sequence length capabilities, adding multilingual support for more languages, integrating 1-bit ideas into multimodal architectures, models that handle text and images,
Oh, interesting.
and even just pursuing more theoretical research to get a deeper understanding of why 1-bit training at scale works so surprisingly well.
So the quest for more efficient AI is definitely an ongoing journey. And bitnet B1.582B4T seems like a really significant leap forward on that path.
It truly does. It strongly suggests that high-level performance in large language models might be achievable with significantly less computational power than we previously thought.
Yeah.
And that potentially opens up a whole new world of possibilities for where and how we can deploy and use these powerful AI tools.
This really makes you think. Could models like bitnet be the key element in finally bringing sophisticated AI capabilities to everyday devices, resource-constrained environments, truly making this transformative tech accessible to a much broader global audience?
It's a compelling thought.
And as hardware keeps evolving to better support these low-bit computations, what other unexpected, maybe remarkable breakthroughs in AI efficiency might we be on the verge of seeing? It's definitely a fascinating prospect to consider.
Indeed. For anyone interested in digging deeper into the specifics, we definitely encourage you to check out the bitnet B1.582B4T technical report on RX4.
Yeah, definitely worth a read.
And you can also find the open source code and a demo page. We'll make sure to put direct links in the show notes for easy access. It's truly fascinating to think about the potential applications of such efficient models across all sorts of domains.